当然我也不用介绍了，这个它实际上是我觉得这个安卓有两个标签了，两套标签哈。一个标签就是 deep learning 是吧？一个 deep learning， 一个包括 Google Brain， 包括 Cat 啊，还有它的 Google Brain 做这个猫啊，这是一套。另外一套就是叫 Coursera 是吧 ？Coursera MOOC Massive Online Open Courses 啊，这也是它新的主推的啊。大概这两套标签啊，来形容这个安卓。好，那今天呢，我们就非常有幸啊，这个请到斯坦福大学的安卓教授给我们做报告，我们欢迎。
Does this work? Let's see. Test. Oh. That kind of works. So, okay. Maybe if I shout into this, that works. So, thank you. 谢谢大家。其实我国语不太好，所以想今天还是讲英语。I think a few months ago, I gave a talk at Baidu in Chinese, and afterward, my friend told me, "Don't ever do that again." So, what I want to do is share with you some ideas about machine learning that I'm excited about. Is this loud enough if I speak like this? Can people hear me okay? Alright. And if I shout like this, does that work?
Yeah.
Okay. Alright, I'll try this. So, what I want to do is share with you some ideas about machine learning that I'm excited about. And this talk is about deep learning. Oh, and I'm curious, how many of you, have taken like have taken my Coursera class or taken one of my? Oh, wow, that's amazing. Thank you for doing that. I've given a lot of talks, but I've never been in a room with this many students that have taken my room. So thank you. That actually means a lot to me. Thank you. And what I want to do is share with you some ideas about machine learning that, namely deep learning, in which we are building large-scale brain simulations and using that to hopefully make learning algorithms much better and easier to use, as well as make revolutionary advances in machine learning and AI. What I'm going to talk about is really not just my vision, but a vision shared with many other researchers. And I think deep learning, these sorts of ideas, is also our best shot at real progress towards the big AI dream. Say a little bit more about that towards the end. But let's start with the basics. So, what do we want computers to do with our data? Right? We have images or video, and we wanted to label or tag the images. Given audio data, we want to do speech recognition. Given text data, we want to do web search, anti-spam, machine translation, and so on. So, a couple of years ago, looking at the first of these problems, I asked some of my students at Stanford to implement a learning algorithm to detect motorcycles. And using the state-of-the-art techniques for that, they implemented a vision algorithm and to detect motorcycles, and this was the result they got. Right. You find motorcycles all over the place, but it doesn't exist. And does this work? Test. This. If I shout into this, is this working? This doesn't work at all, right?
No.
Yes? No?
能请工作人员把那个麦克风打开吗？
先把声音搞大一点。
其实如果我打 actually does this work? So if I tap If I tap the microphone, it seems to do something, but I think the audio on this microphone is very low.
Yeah.
But I guess if I hold it up and talk like this, you can hear me okay?
Yeah.
All right, let's try this. Thank you. Okay, so for all of these applications, I think machine learning is our best technique for building all of these applications, but there's a lot of work to get algorithms to work, and each of those lines is easily anywhere from 6 months to 2 years of work for anywhere from half a dozen to 50 engineers. So is there a way to make learning algorithms easier to use and also make them perform better? In this talk, I'm going to illustrate most of these ideas using images and audio to start because it's easier to talk about. But the ideas are general and also apply to other problems. And towards the end, I'll say a little bit about natural language and text as well. So, why is it hard for a computer to look at this image and figure out what it is? It seems so obvious what that is. How could a computer possibly fail to figure that out? Zooming into a small part of the image where the little red square is, where you and I see a motorcycle, a computer sees this, right? A grid of pixel intensity values. So the computer vision problem is to look at all those numbers and to say that those numbers represent the exhaust pipe of the motorcycle. It seems like it would be a hard problem to do that. In the machine learning world, when guys like me talk about machine learning, we usually say, we'll take the data, take the image, feed it to the learning algorithm, and let the learning algorithm figure it out. But this isn't how learning algorithms actually work in practice, or this actually doesn't work that well for the most part. To explain why, let's pick a couple pixel locations, and I'm going to plot that image on this chart where that image has a relatively dark pixel 1 and a relatively bright pixel 2, and so that motorcycle image appears at that position on the plot. Let's do this for a different motorcycle image. There's a bright pixel 1 and a dark pixel 2, so the appears in the lower right. And if I do this for a couple non-motorcycle images as well, I might get that. If I do this for more positive and negative examples, for more motorcycle and non-motorcycle images, what I might get is a lot of examples that are very jumbled together. And if you feed this as data to your learning algorithm, it's very difficult for your learning algorithm to figure out what is and what isn't a motorcycle. So what is actually done in computer vision is, rather than feed the raw pixels to the algorithm, we usually instead try to come up with an intermediate representation known as a feature representation, and it is that which we feed to the algorithm. In this illustrative example, if we could write a piece of software to tell us whether or not an image has wheels in it, and if we could write a piece of software to tell us whether or not an image has handlebars in it, then your data set would look much more like what's on the lower right-hand corner, and it then becomes much easier for an algorithm to separate out the positive examples and the negative examples, to distinguish what is and what isn't a motorcycle. But the story doesn't end there, because we don't actually know how to write software to tell us whether or not there are wheels or whether there are handlebars in an image. So what is actually done in computer vision is people write software, very complex, opaque pieces of software, to try to capture vague statistical properties of the image. And so, say more about that in a little bit. But so this idea of computing features is pervasive in machine learning, where for images, you have to come up with vision features. For audio, you have to come up with audio features. And for text, you have to come up with natural language features. Given that the feature representation is the primary lens, or is the primary prism through which our algorithms sees the whole world, it gives the feature representation a certain importance, and you have to ask, where do these features come from? So in computer vision, the state-of-the-art answer for where you get features from is there have been teams of tens or hundreds or thousands of computer vision researchers that have spent decades, large fractions of their lives, hand engineering vision features. The image on the upper left, SIFT, S-I-F-T, that's a screenshot I grabbed from the SIFT paper, which is the most widely cited paper in computer vision in the last 15 years. And this is one piece of software for computing features for computer vision. I know the author, I'm friends with the author, David Lowe, and it took David literally 10 years to come up with the SIFT algorithm. And I've read the SIFT paper maybe 5 or 6 times by now. And to this day, I still have no idea what the algorithm is doing. And the reason is David Lowe had taken 10 years to fiddle with the pseudocode, to move pieces of code around, change parameters around, until 10 years later, he wound up with this very complex piece of software that computes very useful features, but it's very difficult to understand what it's doing. And that's how you get the best features from vision today. How about audio? How do you find features for audio processing? Same thing. Teams of tens, hundreds, or thousands of audio researchers hand engineering features for decades. And so the MFCCs, that's a very useful feature, but again, after reading the MFCC papers many years, I'm still not entirely sure what it's doing. And how about natural language? Same thing, right? In fact, a lot of natural language processing research today is unapologetically about trying to find better features. So think about parsers. Why is there so much work on writing better parsers? I don't actually care where the noun phrases in my sentences are. I don't actually need a piece of software to tell me that. But the reason we spend so much time working on better parsers is in the hope that the parser can generate useful features for me to then improve the performance of some downstream application, like web search, anti-spam, or machine translation that I actually care about. So coming up with features is difficult, time-consuming, requires expert knowledge. And if you walk around the technology industry today, if you walk around Silicon Valley or if you walk around the Beijing tech industry, most of doing applied machine learning research today is sitting around trying to hand design better features to feed to your application. So, can we do better? The next piece of what I want to talk about draws from biological motivation. And it was really, there's this fascinating hypothesis that most of human perception, most of how we understand images, audio, text as humans, most of it may be due to not many different hand-engineered algorithms, but rather due to one single algorithm. And perhaps like many of you, I tend to treat biological inspiration with a great deal of caution and even a healthy dose of skepticism. But there's this fascinating hypothesis that most of human perception, most of how we understand data, may be due to one learning algorithm. And I think this gives us a hope that if we can find an approximation to this algorithm and implement it in a computer, that might be a much better way to make progress on computer data understanding, on computer perception. So let me share with you what this hypothesis really means and some of the evidence for it. Shown on the figure, that red piece of brain tissue is your auditory cortex, and if you use it to understand sound. Neuroscientists have done the following fascinating experiment where they can cut the wire in an animal between the ear and the auditory cortex and rewire the signal from the eyes, from the optic nerve, so that it eventually gets routed to the auditory cortex. It turns out if you do this, the auditory cortex will learn to see. And this is the word see in every single sense of how I know how to use the word see. These are animals that can do visual tasks, do visual discrimination tasks, and look at images and make correct decisions, and they're doing it using that red piece of brain tissue. In this figure, that red piece of brain tissue is your somatosensory cortex, used to process touch. If you do a similar neural rewiring experiment, your somatosensory cortex will learn to see. So it turns out there's a wealth of evidence like this that suggests that depending on what data you feed the same piece of brain tissue, whether you feed it sight or sound or touch data, the same physical piece of brain tissue is able to process sight or sound or touch or language or other things. And if the same piece of brain tissue can process sight or sound or touch, then maybe there's one underlying algorithm that can process sight or sound or touch, just depending on what data you feed it. And if we can discover an approximation to this algorithm and implement it, I think that will allow us to make a lot of progress in machine learning. it turns out that the hypothesis, this one learning algorithm hypothesis, has a lot of other evidence. Just to run through this quickly, shown on the upper left is a system that's being developed to help blind people see. The way it works is you strap a camera to your forehead, a low resolution, strap a camera to your forehead of a blind person to take a picture of what's in front of you. You then run a wire to a grid of electrodes that you place on your tongue, and you map a grayscale image to a pattern of voltage values on your tongue, where say a bright pixel maps to a high voltage and a dark pixel maps to a low voltage. And in 10 or 20 minutes, if you wear the system, you will learn to see with your tongue. There are also schools today training blind children to use echolocation or sonar, where you can have children snap their fingers and they learn to interpret the pattern of sounds bouncing off the environment as sonar, so they can walk around just snapping their fingers and never run into anything. Haptic belt. I have one of these in my lab, but you wear a belt with a ring of buzzers around your waist and program it so that the buzzer facing north buzzes. So if that's north, the buzzer here would buzz, and if I turn like this and that's north, then the buzzer here would buzz. And it turns out that just as you know where your hands are, where your arms are, even with your eyes closed, if you wear a haptic belt, which I have, in 5 or 10 minutes, you just know where north is. In the same way that I know where my arms are, even with my eyes closed, wearing this for a few minutes, you just know where north is in the same way. And finally, you can plug a third eye into a frog and that's to do with it. So to surprisingly large extent, it's almost as if you can plug almost any sensor into almost any part of the brain, and the brain will learn an appropriate representation or feature representation for whatever data you feed it. So the question is, can we get a computer to also learn appropriate feature representations automatically for whatever data you feed it? So here's the mathematical formalism of the problem. Given a 14 by 14 image patch X, you can represent the image patch using 196 row numbers with the pixel intensity values. So the mathematical problem is, given that image patch, can you find a better representation? Meaning, can you find a better list of numbers, a better feature vector, with which to represent that image patch other than just writing out the pixel intensity values? In order to do this, I'm going to turn one last time to biological motivation. So it turns out that in your brain and mine, when you see an image, the first thing your brain does is look for edges in an image. So an edge is a light region, like this, adjacent to a dark region, like this. So in your brain right now, there is probably a neuron looking for a 45-degree line or a 45-degree edge, like that shown here. And in your brain right now, there's probably a different neuron that is looking out for a vertical line or a vertical edge, like this. So out of this knowledge, one thing we could do is to try to hand engineer features to try to mimic this. But I think it's more interesting, instead of trying to hand engineer something like this, to see if we can come up with algorithms to learn this automatically. I started working on deep learning when I learned about this fascinating result called an algorithm called sparse coding by two neuroscientists, Bruno Oshausen and David Field. Oshausen and Field are neuroscientists, and when they came up with the sparse coding algorithm, they had published this result as a scientific attempt to explain early visual processing in the brain. But when they published this paper, it was sort of like a mathematical result, like a basic neuroscience result, like an observation on the mathematics behind perception. And they had never envisioned that this would be used as a machine learning algorithm. But it turns out to be an unsupervised learning algorithm, meaning an algorithm that just learns from unlabeled data, and it gives a very good explanation for early visual processing. So let me explain the algorithm. Sparse coding takes as input m images, so x1 through xm, each of which is, say, a 14 by 14 image patch, so rn by n. And what it does is it learns a dictionary of basis functions, phi1 through phi k, let's say 64 basis functions, and it learns it so that each of your input examples x can be approximately decomposed as a weighted sum or as a linear combination of your 64 basis functions, and subject to the constraint that those weights, that those coefficients aj are mostly zero. Okay? The constraint that the aj's are mostly zero is called a sparsity constraint, hence the name sparse coding. So I think this is the only equation I have in this talk. So I hope you enjoyed it. But to explain the same thing in pictures, when you feed a set of natural images to sparse coding, what it will do is learn a set of 64 basis functions, shown in this example by the 64 image patches on the upper right. Given a new test image, what it will do is select out a small subset, let's say 3 out of 64 of my basis functions, and explain my test example as a weighted sum, as a weighted linear combination of, say, just 3 of these 64 basis functions. So, a couple observations. First, sparse coding could have chosen absolutely anything at once for these basis functions on the upper right. It's completely unconstrained. You can choose any basis functions at once. But it turns out, every time you run sparse coding, 100 times out of 100 times, the basis functions will all look like what you see there. They'll look a lot like edge detectors. In other words, sparse coding has, quote, invented edge detection. Second, in this example, what sparse coding is saying is that this image X is 0.8 times edge number 36 plus 0.3 times edge number 42 plus 0.5 times edge number 63. So if you represent the image by that list of numbers, A1 through A64, corresponding to the coefficients, the weights, those 64 coefficients, most of which are 0, then that list of numbers, A1 through A64, gives you a better representation of the image. It gives you a high-level, more succinct, more compact representation of the image. And in particular, that list of numbers tells you what edges appear in the image, and this is a more useful representation. It's better to know where the edges are in the image than to know where the pixels are in the image. So from unlabeled data, let's learn a higher level representation of the image. Here, just a couple more examples, but just to summarize, sparse coding invents edge detection and it automatically learns to represent an image in terms of the edges that appear in it. Other neuroscientists have also compared the edge detectors found by sparse coding and shown that it is quantitatively quite similar, not identical, fairly similar to the edge detectors observed in the primary visual cortex in the biological brain. So sparse coding gives by no means a perfect explanation, but a decent explanation of early visual processing in the brain. And it gives a set of features that are more useful for vision. So that was vision. How about audio? Evan Smith, who was a postdoc at Stanford, ran the following fascinating experiment. He took sparse coding and he applied it to audio data, and sparse coding learned these 20 basis functions. So this is a grid of 5 by 4, so 20 basis functions. So sparse coding learns to explain audio clips as weighted sums of these 20 basis functions. What he did was, for each of these 20 basis functions, he went to a database of CAT, of biological auditory processing. And for each of these 20 basis functions, he found the closest match in the auditory processing system of a cat. So shown in blue here are the output basis functions learned by sparse coding, and the closest matches in biology are shown overlaid in red. So the same algorithm, same piece of software, on one hand gives a very good explanation for early visual processing, and it also gives a decent explanation for early auditory processing. I'm not going to show the slide because of time, but some of my students at Stanford have applied this to explain early touch processing, early somatosensory processing, and it turns out the same algorithm gives not a perfect explanation, but a surprisingly good explanation good model of early somatosensory and touch processing as well. So beyond sparse coding, what we can do is then recursively apply this idea to build even higher levels of representation. So the way we implement sparse coding is actually with a model called an artificial neural network. I'm not going to go into details, but loosely, it's a loose simulation of neurons in the brain where each of the basis functions, each of the 64 basis functions for images, or each of the 20 basis functions for audio, corresponds to a loose simulation of what one neuron in an artificial brain might be doing. So each neuron in the brain is like a feature detector that's looking to find a specific edge or listening for a specific audio, a snippet of audio, or what have you. So with one layer of sparse coding, we can go from the image input pixels to one layer of simulated neurons on top that are edge detectors for the case of images. And what we can do is recursively apply this idea to build even higher and higher layers of representation. So let me show you what this looks like when you do this. When you apply one layer of sparse coding, you can group together pixels to form edge detectors. So what this visualization means is that this little square here, that visualization means that one of my feature detectors, one of my basis functions, or one of my little simulated neurons in my neural network has learned to detect vertical edges that look like that. If you recursively apply this algorithm, you can then learn to group together edges to form models of object parts, and then group together object parts to form more complete models of objects. These results were generated by training the algorithm on a data set that comprised entirely of pictures of faces. And so on the second layer, this visualization means I have a neuron that has learned to detect eyes that look like that. And on the highest layer, this neuron has learned to detect faces that look like that. Okay? A couple technical details. Although not shown here, the highest level neurons actually look at much larger regions of the image than the lower levels of the neurons. So as you go up, each of these neurons look at bigger and bigger regions of the image. And because of the way of the visualization, this isn't clear, but each of these neurons is actually computing a very complex nonlinear function of the image. It's just that we visualize what the neuron is looking for as an image. But the multiple layers of sparse coding actually are feature detectors that become increasingly complex nonlinear functions of the input as you go up this hierarchy. So, training on unlabeled data, we can learn very rich feature detectors, right? We can learn feature detectors to look for faces or for other objects. So what is it good for? Here are some machine learning applications. Suppose you want to go back to the original problem and write a piece of software to recognize motorcycles. The standard machine learning approach to this would be to collect a lot of examples of motorcycles and collect a lot of examples of non-motorcycles and apply a supervised learning algorithm, maybe with hand-engineered features in order to learn to distinguish between the two classes. But now, with sparse coding and the recursive versions with deep learning, we can now augment our data set with a lot of unlabeled data to suck down a lot of random unlabeled images off the internet. Maybe some of these images are motorcycles, maybe they're not, we don't know, it's unlabeled data. And we can then use our essentially infinite source of unlabeled data to learn better features for images, like face detectors, wheel detectors, road detectors, grass detectors, head detectors. And having learned a rich set of features, we can then use these features, learn from unlabeled data, but use the features together with a small amount of labeled data with which to learn to classify what objects are, with which to learn to classify motorcycles versus non-motorcycles. So one of the first data sets we looked at that we ran this on was a video activity recognition benchmark called the Hollywood 2 benchmark. This is one of the hardest benchmarks in computer vision, where the task is to watch a short video clip and decide whether or not the video clip contains, two people kissing, two people hugging, someone driving, someone eating, to recognize activities in videos. Over the last few years, researchers in computer vision have hand-engineered and tried a lot of different features and made progress from, like 38% up to 46, 47% accuracy. one of my students at Stanford decided that instead of hand engineering the features, he would just try to learn them. And immediately, he was able to substantially outperform the previous state-of-the-art in computing. More broadly, for application after application in audio, images, video, natural language, deep learning algorithms, these sorts of algorithms for learning features, have been knocking over benchmarks very rapidly. In my entire professional life working in machine learning, I have never before seen any one technology knock over this many benchmarks this rapidly. This is just a few examples. Many research groups, really not just mine, but many research groups have been using these technologies to knock over benchmarks like crazy. And I should say, right here in Beijing, one of the leading groups in deep learning is in Baidu, where Yukai leads the deep learning team that has done. I don't know if I have permission to talk about what products and applications he's worked on, but Yukai, Baidu really, is one of the leading groups in deep learning and has knocked over tons of benchmarks and is making Baidu products that you're probably using work quite a lot better. So, after getting to the stage that I showed you on the last slide, about 2.5 years ago, I sat down with my students and we spent a lot of time thinking through the question of how do you build a high accuracy learning system? Given where we are with deep learning technology, how do we take it to the next level? And for inspiration, we started looking back in the history of machine learning. We actually look back to around 2000, 2001, when most people were doing supervised learning, so learning from labeled data, where to label all the data and then feed that to the algorithm. And back in the day, back in 2000, 2001, the debates were on, given the leading learning algorithms of the day, memory-based algorithms, winner perceptron, naive-based, what is the best algorithm? So my thinking has been heavily influenced by a study done by Banco and Bro in 2001, where they took the leading learning algorithms of the day, supervised learning algorithms, and they ran a study comparing the effects of running different algorithms on different amounts of data. And their result is shown on the upper right, where the 4 different lines correspond to 4 of the leading learning algorithms of the day. And the result is very clear, right? As you give the algorithms more data, the performance goes up. And very often, a supposedly superior algorithm will outperform a supposedly inferior algorithm. A supposedly inferior algorithm will outperform a supposedly superior algorithm if you can give the supposedly inferior algorithm more data and just scale it up to a bigger data set. And so results like these have led to a saying in machine learning that often is not who has the best algorithm that wins, is who has the most data. So this is the result in supervised learning where data was really limited because it's a lot of work to label data. How about algorithms like sparse coding where we can learn from unlabeled data? With unsupervised feature learning, with algorithms like sparse coding, we can learn from unlabeled data. So all of us have access to an infinite source of data. You can suck down as much data as you want off the web. And so it's no longer who has the most data that wins, it's who has the most computers, or who has the computational capability to process the essentially infinite amounts of data that all of us now have. So one of my students, Adam Coase, ran an experiment in which he took the leading learning algorithms, the leading unsupervised feature learning algorithms of the day, and shown in the different lines. And the trends here are again very clear, where the algorithm matters a bit, but it's really the bigger you can scale these algorithms, the larger you can scale these models as shown on the x-axis, the better the performance. So given these results, we spent a lot of time thinking through how can we take the unsupervised learning algorithms, the sparse coding, the deep learning algorithms, and what would it take to build really large-scale versions of these models. So I spent some time in Silicon Valley. I spent some time wandering around Silicon Valley trying to figure out where can I get access to a lot of computers in order to build really large deep learning algorithms. And I guess in order to explain what we did on building very large deep learning algorithms, I'm going to break the next part into two pieces. It turns out that when guys like me give talks on deep learning often combines labeled data and unlabeled data, where we use unlabeled data to learn the feature representation, and then we combine that with some labeled data to come up with the classification predictions. And wow, okay. Oh, wow. No. Does this? No. Okay. Does this still work? All right, still works about the same as before. Right? Okay. So it turns out when you hear people give talks on deep learning, very often the supervised learning or labeled data and the unsupervised learning, unlabeled data results are often conflated, and it makes a very turns out it sometimes makes the talk sound better, but it makes the results very confusing. So I'm going to deliberately separate out these two things and talk about applications where the performance comes from being able to exploit having a lot of labeled data, and then later talk about results where the performance comes from being able to exploit a lot of unlabeled data. I'm going to start with learning from labeled data. And so what we did was we developed, and so in 2011, I started a project at Google to take advantage of Google's distributed network infrastructure to build very, very large neural networks, to build these deep learning algorithms, starting with exploiting labeled data. So given a neural network like that, like one of the network models that you saw, what we would do is take the model and partition it so that different parts of the model can live on different machines. And if you do that, then because the number of network connections we're cutting across is relatively small, there's some amount of communication that needs to take place across the different machines, but not an excessive amount. Within each machine, we then further exploit multi-core parallelism. If each of the machines has 16 cores or something, then we can further exploit multi-core parallelism within a single machine to speed up the algorithms. So with this form of parallelism, we did the learning using stochastic gradient descent, or mini batch stochastic gradient descent, for those of you that know what that is. And it allowed us to parallelize our models across on the order of 100 machines, so maybe 1,600 cores. But this still wasn't good enough for us. We wanted to layer on another layer of parallelism, where we don't just take a single model and distribute it across 100 machines, but we want to layer on another layer of parallelism. So to do that, what we did was take the model that we have shown up there. I'm drawing this as though it's partitioned across 4 machines, but we're actually partitioned across maybe 100 machines. But what we'll do is we take the model and we will implement what we call a parameter server, which is a set of machines that keeps track of all of the parameters of our entire model. What this copy of the model shown on the lower left will do is it will download from the parameter server a copy of all of the parameters of my model. It will then take some of the data and do some computation, like figure out how to take a learning step. Mathematically, there's one stochastic gradient descent step. It does some learning to compute some update delta p that it wants to implement to the parameters. And then the parameter server will take the delta p from my model and add it to the global copy of the parameters. And then it will transmit p prime, get a new update, and sum it up again. And this is how learning proceeds. And what this allows us to do is make multiple copies of this model workers, with each of those copies at the bottom comprising maybe 100 machines. And each of my model workers at the bottom will proceed in parallel, with each of my 3 copies at the bottom will work on a different 1/3 of the data. And I've drawn this here as though we have 3 model workers. In practice, we have anywhere from 10 to 50 model workers. And so, from an engineering standpoint, one huge advantage of using this parameter server setup is that if one of my slave models, if one of these three pieces at the bottom goes down, the rest of the model can keep on running. So it turns out that with our computers, the mean time to failure of like your desktop computers may be 3 years. The computer fails on average every 3 years. What that means is if you run on 1,000 machines, 3 years is about 1,000 days, right? So what that means is if you run on 1,000 machines, you have about one machine fail every day. Because of preemption and other problems, we actually have machines fail much more often than one day. But with this sort of architecture, if one of the machines is very slow because something goes wrong, because with 1,000 machines, there's just much higher variance in the response times of the machines. If one of the machines goes down, or one of the shards goes down, or one machine is very slow and times out, we can just discard that shard, and the rest of the computer, the rest of the cluster, can keep on making forward progress. When you work with thousands of machines, one of the issues you have to deal with is just the high variance. Some machines will just respond much faster than others because of weird things to do with the router or the memory, or some machines are swapping or what have you. And this architecture makes us much more robust to that. And so, using this model, we are able to do two things. The first and more interesting thing we could do is train very large models. With 100 machines, by taking one model and spreading one model across 100 machines, we can train models that don't even fit in the memory of a single computer. So we train massive models. The second thing it does is even when we train very small models, it allows us to run much more quickly. So here we did a comparison with training on a cluster versus training on a single GPU. So only very small models will fit on a GPU, on a graphics processor unit. We found that even compared to GPU training, by distributing our model across 10,000 cores, we can substantially train much faster than is possible on GPU. But even more interesting is the fact that by distributing these models on so many machines, we can train models that don't even fit in a single computer. Certainly don't fit in a single GPU. So let's see. So what is this useful? What is this useful for? Again, we're going to separate out the results from what we did on supervised learning on labeled data from what we did on unlabeled data and unsupervised learning. So I'm actually curious, how many of you use an Android cell phone? Oh wow, okay, cool. So here are a third of you. So if you use the Android cell phone speech recognition, it's actually built on top of this deep learning architecture that my team built at Google. To give credit where it is due, just really the work of Vincent and Luke, who is part of the speech team at Google. But working with my team and building on top of this architecture, Vincent and Luke's team was able to substantially reduce the word error rate of the Google speech recognition systems. Like over about a 20% error reduction in the word error rate by applying these deep learning algorithms to massive amounts of labeled speech data. Other applications is also used in Google Street View to read street signs and so on. And then there's a bunch of other applications within Google that I shouldn't talk about, but that I think will make Google a lot of money, and we'll hopefully we'll make a lot of users' lives better. And I think Yukai doing something working on different applications at Baidu as well, which I think will make Baidu products work much better. He's already. So talk about the applications of learning from labeled data. How about learning from unlabeled data? So, right, you saw this result where the bigger we can scale our models learning from unlabeled data, the better it performs. So one of the in computer vision, before I joined Google, before I started this project at Google, in computer vision, people were often training on 50,000 images, and there were like maybe 32 by 32 images. And the very biggest models people would train on were maybe 10 million parameters. 1 million was very big, and 10 million was actually bigger than anyone else they trained at the time. By taking the models and running it on Google's distributed cloud infrastructure, we were not training on 50,000 images, and we were not training on 10 million parameters. We were training on 10 million images and large images, so 200 by 200 images. And instead of 10 million parameters, we train models with 1 billion parameters. So literally 100x bigger than the previous state-of-the-art. And so one of the most fun experiments we did was we trained this algorithm on YouTube videos. So imagine, if you will, that we have this, little simulated baby brain with 1 billion parameters. What we did was we took our little simulated newborn baby brain and we made it watch YouTube for a week. And training on 1600 CPU cores. After a week, we would then examine our little neural network to try to figure out what it had learned. So we had a hypothesis that it will learn feature detectors. These individual neurons will learn to detect different features, and some of the feature detectors we hypothesized will learn to detect common objects in YouTube. So faces occur commonly in YouTube, and we looked at the neurons, and we found that, lo and behold, one of the neurons was a face detector. So these are the neurons, these are the images to which one particular neuron responded the most strongly, shown on the left, and shown on the right is the input that most strongly activates this neuron. So we really have a feature that is a face detector. And we also documented that this face detector, is fairly invariant to rotations, translations, and so on and so forth. So faces occur commonly in YouTube, so that we found a feature detector for that. What else do you think occurs commonly in YouTube?
Cats.
Cats. And we looked and we found that, lo and behold, we found a different feature detector that had learned to detect cat faces. The remarkable thing about this was no one had ever told it what a cat is. It had invented the concept of a cat by itself. Now, detecting cats is a useful technology demonstration. It is a nice technology demonstration, but what's this actually useful for? One of the things we did was we applied it to image classification. ImageNet is the largest computer vision benchmark in academia, and the task is to examine an image and decide which of 22,000 object classes the image is. It's a very difficult task. One of the tasks, or two of the categories, are stingrays versus manta rays, and the vision algorithm has to look at an image and decide is this a stingray or a manta ray. Another two classes are isosceles triangles versus equilateral triangles. How do you distinguish amongst them? I think that human performance on this data set, given how difficult and almost ambiguous a lot of the examples are, I would guess human level performance on this might be around 30%, but that's a gut feeling number rather than one that's substantiated by figures. It's very hard to resolve. So, if you start working on this, well, I guess with 20,000 classes, if you guess randomly, your accuracy is 0.05%. Previous state-of-the-art was 9.5%. What we did was we learned the features from YouTube, so learned features from a ton of unlabeled YouTube video. We then took those features and combined it with a small amount of labeled data for the 20,000 object classes. And doing that, our accuracy was 21.3%. Our research paper says 15.8%, which is what it was when we published the paper, but since then we brought up the performance substantially. And so this is a significant improvement on computer vision object detection. Beyond this, it is now being rolled out, I guess, in a number of other applications within Google as well. So, before wrapping up, there's just one last piece that I want to talk about very quickly, which is the application of these ideas to natural language. And I guess I want to talk about that because I know there's a lot of NLP research going on in Tsinghua and also in Beijing. And it turns out that there are some very interesting ideas on adapting these algorithms to language, which is one of the most important applications of it. So the ideas here are a little bit different. Let's share with you what it looks like very briefly. So before diving into how we apply deep learning to language, I want to just describe one idea, which is the idea of learning feature representations for words. So given a word like Monday or a word like Britain, one way to represent the word is with this one on or one hot vector. You can do 0, 0, 0, and 1 in one position. But this isn't a great feature representation for words. So it turns out there's a literature on learning features for words, and it's like this is sometimes called distributional representations. There are other papers, various ways of doing this that I don't want to talk about. But the idea is, for each word, we're going to come up with a low-dimensional feature vector. So the word Monday might be represented by the feature 2,4 plotted over there, and the word Britain might be represented by the word 9,2, let's say. And with these algorithms, the word Tuesday might then be represented by a feature that's similar as Monday. So it's 2.1, 3.3, because Tuesday and Monday are kind of similar things. And the word France might be represented by feature vector similar to Britain, and the word on will be represented by yet another feature vector. So now, given a sentence like on Monday, Britain, blah, 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 you will represent the words using those feature vectors that we pull up from the figure on top. So, I'm showing this with two-dimensional feature vectors, so I can plot it. In practice, 100-dimensional feature vectors is more common. There are various ways, like LDA, OSI, LSA, distributional representation, neural language models, various ways to come up with these feature vectors. I don't want to talk about the specific ways. I just want to build on top of it. Okay? So, given a sentence like "the cat sat on the mat," what we can do is pull up a feature representation for each of these words. Now, imagine that you want to apply a deep learning algorithm to this. You can the straightforward approach would be to stack on top of this a set of neurons to try to learn representations for different parts of the sentence. But now, if you look at that node, right, where the arrow is pointing, that node sees the three words "cat sat on." So, it's the job of that node in the network to learn a feature representation for the phrase "cat sat on." But the phrase "cat sat on" doesn't mean anything, right? It's not a proper English phrase, so I don't know what it means to learn a feature representation for the phrase "cat sat on," because it doesn't mean anything. So for language, I think we should instead come up with an algorithm that respects the natural hierarchy that sentences come with. There's the parse tree structure. So in this sentence, the cat is a phrase, the mat is a phrase, on the mat is a phrase, and so on. And so if you look at that node, it's the job of that node, PP stands for prepositional phrase. It's the job of that node to learn a representation for the phrase "on the mat." And "on the mat," that is a proper English phrase. And we can think about how we can come up with software to learn a good representation, a good feature representation for the phrase "on the mat." So, how would you represent the meaning of the phrase "on the mat"? We've been learning all of our representations using feature vectors. We represent images as feature vectors, we represent audio as image features, we represent words with feature vectors, so we're going to represent phrases with feature vectors. And so the job of the algorithm is to come up with a feature vector, maybe 8,3 here, to represent the meaning of the phrase "on the mat." So let me illustrate what we want. This is an illustration, so this is aspirational. This is what we would like to do. I'm not saying we could do this. What we'd like to do is have an algorithm come up with a representation for the phrase "the day after my birthday," that is, let's say 3-5, that would map there, that is maybe similar to Monday and Tuesday. And given a phrase like "the country of my birth," we'll hopefully learn a feature representation 9-3 that would be close to Britain and France, because the country of my birth is something that's similar to Britain and France. So how do we do this? How do we come up with that number 8-3? So I'm going to color in some of these nodes just for the purpose of illustration. And the way we're going to learn these representations for phrases is we're going to use a neural network. So we're going to build a neural network that takes as input the two children nodes, so the 3-3 and the 8-5. And it's the job of the neural network to output two things. First, it should output a yes or no to tell us whether or not those two children should have a common parent. In this case, the answer is yes. Or those two nodes should have a common parent because that forms a valid phrase. And second, the neural network has to output the semantic representation, has to output the feature representation you want to use to represent this phrase. So, having trained this neural network, if you're given a new English sentence, you can apply the neural network here and ask, is the cat a phrase? The answer is yes. And the representation of the phrase "the cat" is maybe the vector 5-2. Is cat sat a phrase in this apostrophe? The answer is no. Is sat on a phrase? No, no. And the mat is a phrase? Yes. And the representation of that phrase is please be. You can then build up your representations, one layer of representation like so. And now you can apply your neural network again. The cat sat is not a phrase in a sentence, sat on is not, but on the mat is, with representation A3. So you can now, you can now build up your representation and so on until you've built a representation for all of the nodes in your apostrophe. I drew this illustration, I did this animation as though we make these decisions greedily from the bottom up. For those of you that are familiar with pauses, you can actually use dynamic programming to do top-down and bottom-up inference, so the pausing isn't entirely due. So the advanced extension of this case. So now what we have is for every word, every phrase, and for the entire sentence, we can come up with a feature vector to represent the semantics, or the meaning of that English phrase. And so what we did was, to try to figure out if these representations are useful, what we did was we took a sentence, which we call the center sentence, and we computed the feature representation for this center sentence. So both took further hits yesterday. We computed the feature for that. And what we did was we looked through our corpus, looked for our set of English sentences, and we found the sentences with the closest feature, with the most similar feature representation as the center sentence. And we list on the right the 4 feature vectors with the most similar feature representations. So the other things that most similar to both took further hits yesterday is we're in for a lot of turbulence, and so on. It thinks that Columbia, South Carolina is similar to unknown word California. Even though it's never seen this word before, it knows that unknown word California is probably a city in the United States and is therefore similar to Columbia, South Carolina. Here are a few other examples. Right? Has declined to comment is similar to coastal within disclosed terms. These two phrases don't have a single word in common. We were lucky is similar to it was chaotic. And so these are feature representations that are getting at a bit of the semantics, and certainly the syntax, but also a bit of the semantics or the meaning of these phrases as well. We did all this work in English. As far as I know, I'm not aware of anyone that has taken these ideas and applied them to Chinese yet, but I believe that all of these ideas will work well for learning semantic representations for Chinese as well, where you can recursively build up feature representations for the meanings of different phrases, words, phrases, sentences in Chinese. But that would be something very interesting to try to build those. What are these features good for? We apply these sentences, these feature representations, to a number of more semantic tasks. So the paraphrase detection challenge is a problem in natural language processing where the goal is to look at 2 sentences and decide that the 2 sentences mean the same thing, or they're paraphrases of each other. Over the last N years, natural language researchers have hand-engineered a ton of different features, and there's some amount of progress from like 79 to 83% maybe. By using this representation to learn the features, we're able to immediately outperform all of the hand engineering that natural language processing researchers have been doing. We've actually applied this representation to a ton of different benchmarks in natural language processing, from text classification to sentiment classification to some things together retrieval, and on I think pretty much every natural language processing benchmark that we've applied this to. I'm sure there's some benchmarks where we did not beat the previous state of the art, but I have a hard time remembering any right now. So it's just worked amazingly well for all sorts of text problems. And the thing that excites me is sentiment classification. One of the benchmarks we use is the problem of looking at a piece of text and judging if this piece of text is like a thumbs up or a thumbs down opinion. Is a positive sentiment or a negative sentiment about something. This is a very hard semantic task, to understand a piece of text, because there are phrases like not good, which means something totally different than good. If you look at movie reviews, they use phrases like not awesome, or not too bad, or pretty good. And to combine the meaning of all of these different words so that they correctly interpret what not too good means. The algorithm has been able to automatically learn to combine words to figure out what the right semantic representation of phrases like "not too good" really means. And so we're starting to apply these sorts of representations to other problems in text as well, mostly in English, but hopefully in other languages as well. So, just to wrap up, I want to just take a slight digression, say a couple words on my philosophy on why I'm excited about these sorts of algorithms. Depending on the application, sometimes when I talk to people, there will be some individuals that will look at a specific application and try to say, how much of the performance of this application is due to human ingenuity, where we sit down and just engineer a lot of our knowledge about the problem into a system, and how much of a system's performance is due to the data or due to the learning algorithm. And for many problems, the data/learning contributes more, but for some problems, maybe today, fewer problems. Maybe there's some problems where you could say human ingenuity is contributing more to the performance of the system than the data and learning. And so, some people look at a snapshot like this and say, human ingenuity is working more for my problem than the data/learning, so we really should just invest in more hand engineering. But for many problems, depending on your problem, I think it's naive to look at a single snapshot in time. Because if instead you look back at history, at the last 5 years or the last 10 years of our industry, I think that human ingenuity has been slowly increasing the performance of our algorithms. Right? We come up with smarter algorithms every few years. Every year there's a conference and the algorithms get a little bit better. So the performance due to human ingenuity has been going up steadily. But I think the performance due to the data, the contribution of the data, has been going up at a much faster rate, just because all of us have access to so much more data now than we did even a couple of years ago. And when you look at two curves like that and extrapolate into the future, the question is, which of those two curves would you rather be on? Right? Which horse are you going to bet on? And extrapolating into the future, I think it's clear that algorithms will continue to get better. Like human ingenuity will slowly get better. The one page of pseudocode you get from a conference paper, that one page of pseudocode will get better, but it will be limited really only to one page of pseudocode for the foreseeable future. But the volume of data we have is growing so rapidly that I think the algorithms that really matter for the future, where I would invest my effort, is in algorithms that can continue to exploit the massive amounts of data that we already have, and that will become even bigger in the future. And I think this really is the secret to why deep learning algorithms work well. That both for the supervised and the unsupervised pieces, they happen to be a class of algorithms that are able to exploit huge amounts of data, and the performance just gets better and better as you give it more data. Maybe deep learning algorithms are not the only class of algorithms with this property, but I think if you're doing research on machine learning or vision or NLP or whatever, I personally tend to focus on algorithms that can exploit the growing volume of data that all of us have and will continue to have. Because that's what I think is almost important, critical for your work to remain relevant going into the future. And just to finish up, deep learning is this idea of let's try to learn our features rather than necessarily hand engineer them, using labeled or unlabeled data. And to close with kind of a personal story, I guess, way back when I was in high school, or way back when I was in secondary school, I was 15, 16 years old, I always wanted to work on artificial intelligence. I always wanted to work on AI. I thought building intelligent machines was like the coolest things you could do. And I don't know how many of you have had those similar AI dreams, right? Like building really intelligent machines or solving the big AI problem. So that was when I was 15. Then I turned 17, 18, and I went to college. And I learned how hard artificial intelligence really is. And then I gave up, right? The field of AI has been around for over 50 years now. And for most of those 50 years, our progress towards building really truly intelligent machines that can do a lot of the things that humans can, our progress has been very limited. So for most of my professional life, I was actually pretty down on the AI dream. And as a Stanford professor, if a Stanford freshman comes to me and says, "Oh, I want to work on a big AI dream, build really intelligent machines," I would say, "Well," and I wish I hadn't said that to the Stanford students now. And frankly, it was only about 5 years, it's about 6 years ago, learning about the latest results in neuroscience and seeing the latest results in machine learning, results like sparse coding and algorithms, this idea, the neural rewiring experiment, suggesting that maybe most of human perception may be a single learning algorithm. It was really seeing those ideas about 5-6 years ago that for the first time in my professional life, I felt like we might actually have a shot at making some progress towards the big AI dream. It's not going to be easy. We don't have the right algorithm yet. It's not going to be 1 or 2 years. It might be decades. But seeing some of the latest results in neuroscience and machine learning and the ability of our algorithms to do amazing things and mimic some computers in the brain, I feel like we might have a shot at making some progress over large numbers of years. Thank you. And in the short, and that's what really excites me. But in the short term, though, I think I'm also very encouraged that deep learning algorithms, at Google, I stepped back from my role at Google about a year ago, but at Google, at Baidu, it's a very good deep learning team there. At various companies, and in lots of academic research group as well, in NLP, vision, other applications. I'm also encouraged that these techniques are already making substantial progress and helping us to get a lot of applications to work. So for a lot of short-term applications you might want to build, I think this is also a very promising technology. And finally, I know that a talk like this, right, it's very high level, the pictures are very pretty, but then when you go home and you're asking, okay, what do I do now to get this to work myself? A talk like this isn't the best medium by which to convey that sort of information. So starting a couple years ago, my students and I put a lot of work into creating a tutorial on deep learning, and the URL is given there. But if you work through the tutorial with the exercises and so on, then you will have implemented, a bunch of this nearly state-of-the-art or state-of-the-art algorithms, and you will have implemented and gotten a bunch of these algorithms to work for yourself. And recently, thanks to Duncan, who recruited both friends, he and I were rambling 20 years ago. Thanks to Duncan, who recruited a team of recruiters here. There is now, it's not linked to yet, but there's a Chinese translation of that wiki as well, so you can work with the tutorial and do the exercises in Chinese. So I hope that for those of you that are interested in pursuing this area of research, either to apply these ideas to your own work in industry or in academia, or to help push forward the state of the art, I hope that working through that tutorial will get you up to the state of the art and leave you well qualified to either apply these ideas or work on pushing forward the state of the art. So with that, let me say thank you very much.